The next graph that we're going to be considering is the cosecant graph. And actually for the cosecant, I'm going to rely heavily on the sine graph, and here's why. If you recall, cosecant of x is the same thing as 1 over sine of x, because secant and cosecant are reciprocals of each other. So when I'm calculating what is cosecant at 0, for instance, I'm actually going to be plugging it into 1 over sine 0. So let's do that. What is 1 over sine of 0? Well, go back to page 1, look at the first entry of the table. We said sine of 0 is 0. So this is 1 over 0, which is undefined. Okay, so maybe at this point we're not too sure what's going on here for that point. So we'll just draw a question mark and we'll come back to it to see if we can figure out what to do about that point. The next one is pi over 4. So I'm going to try to evaluate what is 1 over sine of pi over 4. Now if you recall, sine of pi over 4 was radical 2 over 2. So if I take the reciprocal of that, I'm going to end up with a 2 over radical 2, which if we punch into the calculator, 2 over radical 2 will give us approximately 1.4. So I'm going to plot the point pi over 4, comma 1.4, where again, this is an approximation. So over here on the graph, we're missing all of the tick marks that deal with multiples of pi over 4. So let's draw those in. We already know what they are. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and that would be the last one because then we have 8 pi over 4, which is 2 pi. Okay, so at pi over 4, we reach 1.4. So here's 1, this is 1.5, so 1.4 is going to be slightly below that. Okay, then what happens at pi over 2? Well, then we have 1 over sine of pi over 2, and if you take a look at pi over 2, sine of pi over 2 is 1, so here we simply have a 1 over 1, which is 1. Okay, so at pi over 2, we reach 1. Then at 3 pi over 4, again, we're considering 1 over sine of 3 pi over 4, which is going to be, well, at 3 pi over 4, we have radical 2 over 2. So this is going to be 2 over radical 2 when we take the reciprocal. That means that we have the point 3 pi over 4, comma, approximately 1.4. That's what we found when we're considering pi over 4. So we'll get this point that should be at the same level as the point at pi over 4. Then at pi, we have 1 over sine pi, which is going to be what? Let's see. Sine pi is 0. So we have that undefined again. Okay, so something is happening, but we don't know what exactly it is yet. Okay, then at 1 over sine of 5 pi over 4, if you look at 5 pi over 4, we're going to get the negative radical 2 over 2. So if you flip it to get cosecant, you're going to get negative 2 over radical 2. So that'll mean that we'll have point negative 5 pi over 4, comma negative 1.4, right? Because 2 over radical 2 was 1.4, and if we have a negative, well then we just prepend it with the negative. At 3 pi over 2, sine of 3 pi over 2 was negative 1. So that means that this will be a 1 over negative 1, which is negative 1. So at 3 pi over 2, and actually I forgot to plot this one, so let me plot this one first. So at 5 pi over 4, we have a negative 1.4. This is negative 1. This would be negative 1.5. So negative 1.4 would be slightly below it, or slightly before it, I should say, slightly above it. And then at 3 pi over 2, we reach negative 1. And at 7 pi over 4, we're going to take the reciprocal of negative pi over 2. So this, negative radical 2 over 2. So this is negative 2 over radical 2. That means that we're going to get a 7 pi over 4, comma, negative 1.4. So that'll be here. And finally, at 2 pi, we got sine of 2 pi is 0. So if we try to find the reciprocal of that, that is going to be a 1 over 0, which is undefined. Okay, so again, there's that question mark of what happens there. Okay, so in order to figure out what is going on, let's try to instead find something that is, cosecant of an x value that is very close to 0, but a little bit greater than. So what I mean by that is maybe we can try to find 1 over sine of like 0.1, let's say. And 1 over sine of 0.1 gives me 10. So that would mean that very close to 0, I get a number that's very high up, or at least in the window of this graph at 10. Let's try to get a little bit closer. So if I do sine of, or 1 over sine of 0.01, then I get 100. And if I try to get even closer to 0, let's say 0.0001, we get 10,000. So what's happening is that as we come closer and closer to 0, okay, from the right-hand side, meaning we get something that is still greater than 0, but we get really close to 0, the graph shoots up because we start getting these very high numbers. And then as we go away from 0, we're going to start coming down to this value that we found of 1.4. And just to prove it to you, let's test something that's close to pi over 4 but less than it. So if I do pi over 4, that gives me 0.7853. So let's test what happens at 1 over sine of 0.78. Say. So that would be like 0.78000, which is less than pi over 4. Okay. So I get 1.421, which is going to be a little greater than what we had at sine of 1 over sine of pi over 4. So what we see then is a behavior like this. And then it goes down to that 1, comes back up to 3 pi over 4, and then something, again, weird happens at pi. Well, let's try and get really close to pi from the left-hand side, meaning we're going to plug in a value that is less than 3 pi over 4, less than pi, which is 3.1415, but is still less than, something that's close but less than. So for instance, I could try 1 over sine of 3.1415. And wow, that's a very large number, 10,792. If I try to get even closer, let's see what is pi. Pi is 3.141592. Let's see what happens if I have 1 over sine of 3.141592 with zeros after it. So I'm getting closer and closer to pi. That gives me 153, not even 1,530,011. So as we get closer and closer to pi, these numbers start getting larger and larger. Okay. But the funny thing is we never actually have the graph cross this. If we were to draw a vertical line, it never crosses the vertical line passing through pi because it just continues to grow larger and larger, and then at pi it's undefined. So the behavior that we're seeing here is special, and we actually draw vertical lines at the places where the graph is undefined. These vertical lines attract the shape of the graph. Okay, so the graph will go towards those lines, but they never cross, and they're called asymptotes. Okay, so here, I'm going to label this asymptote. Let's see what happens as we get close to pi from the right-hand side, though. That means that I'm going to try to plug in a value that is larger than pi, but close to pi. So again, remember, pi is this 3.141592. If I want to plug in something that is slightly larger than this, I can try to plug in 3.142, right? That's going to be a little bit larger than that, and then see what that gives me. And notice that's giving me a very negative number, negative 2,454. If I try to get even closer, so maybe if I do 1.1416, because this is still larger than pi, but closer, then it starts to get more negative. Okay, in this case I have negative 136,120. So on the right of this vertical line, the graph is going to go down to negative infinity, and then it'll go and meet these points up to, it'll reach up to a maximum of -1, then it'll go through the negative 1.4, and as we're getting close to 2 pi, which is the other place where we had undefined, we're going to get that the graph is going to go down to negative infinity again. Okay, again, we haven't shown it, but we can do so on the calculator. 2 pi is 6.2831. If I try to look for a number that is less than 2 pi, but still pretty close, I can plug in 6. Let's say 2800, right? That is less than that number, but close. And I see that we get negative 313. So if I try to get even closer, let's say like 6.2831, right? It starts to get more and more negative. Okay. Right, so that's going to go down to negative infinity. Right, so the moral of the story is anytime you have undefined, you're going to have an asymptote. And that asymptote is going to attract the shape of the graph. So just to define it, an asymptote, this is going to be a line that attracts the shape of the graph. In the case of cosecant, it corresponds to places where the function is undefined. And in general, that's going to be true. If a function is undefined, then that likely means that, or not likely, you will have an asymptote at that x value. Okay, so in this case, we say x is equal to 0 is an asymptote, and x is equal to pi is an asymptote, x is equal to 2 pi is an asymptote. And what I want to do now is extend the cosecant graph. And instead of bringing over or copying over the one cycle that happens between 0 to 2 pi, I want to give you some tips that can help you graph this a little bit more quicker. You want to start by drawing the sine graph as reference. Okay, so what that means is, well, I'm going to plot 0, 0 because that is a point on sine, and then at pi over 2 we reach 1, at pi we reach 0, at 3 pi over 2 we reach -1, and then at 2 pi 0, and after that it repeats, right? So at 5 pi over 2 we go up to 1, at 3 pi down to 0. Going into the negatives, we go -1 at -pi over 2. Then at -pi we reach 0, then 1 at -3 pi over 2, then 0, -1, and 0. So what I'll do is I'll draw sine kind of dashed because again this is only our reference graph. This is not ultimately the graph that we're interested in. We're just using it to help us with cosecant. So that's the first step, draw sine as a reference. The second step would be to draw asymptotes that wherever we have zeros for sine. And now why would we want to do that? Well, remember, cosecant is a reciprocal of sine. So if sine has 0, so for instance here it has a 0, or at pi it has a 0, then 1 over that 0 is going to give us undefined. So that is going to correspond to asymptotes. That means that we have 1 here, 1 here, here, and same in the opposite direction. Okay, and then finally the last step. You want to flip, and here I'll use quotes, like you want to flip the shape of sine. The shape of the graph of sine, that is. Okay, so what I mean by that is if you have between 0 and pi the shape of the graph going downwards, then we're going to flip to create an upwards parabola that has the vertex at 1. If you have the shape of sine facing upwards or going up, then we're going to flip that and make a downwards facing parabola for cosecant. Okay, so ultimately what we get is the following. Okay, so what are the characteristics of cosecant now? Well, as far as a domain, we have to place restrictions because there are places where cosecant is undefined and we don't ever want to have x values that cause undefined y values as part of our domain. So That means that in the domain, we'll have everything from negative infinity to positive infinity, except the places where we have multiples of pi, because at multiples of pi, we have asymptotes. Okay, so except where x is equal to n times pi, where n can be any positive or negative integer or 0. What about the range? Well, the range is a little different now too, because, well, before we had a minimum y value of negative 1, a maximum y value of 1. That is no longer the case, right? Now we can get very negative y values, and we can also get very positive y values. So the graph can extend all the way down to negative infinity, but it can also go up to positive infinity. The only place in the along the y-axis, or I should say the only y values that are never touched by the graph, is y values between 1 and negative 1. Right here we see a little strip where there is nothing that touches the cosecant graph, right, in this area here. So for the range, we're going to say we can have anything between negative infinity up to negative 1, right? The graph can touch any place from negative infinity up to negative 1. But after that, there is nothing until we reach 1, and then out to infinity, we start seeing the graph again. So because we have two disjoint areas in which the graph exists, we actually use union. And this is a symbol that was introduced in your algebra courses. When you have two places that do not overlap, that are part of a solution set, we use union. In this case, it's not necessarily that it's part of a solution set, it's just part of where we see the graph on the y, if we're considering y values. Okay, what about amplitude? Well, amplitude would mean half the distance between the maximum y value and the minimum y value. But in this case, the maximum y value is never attained because this goes on to infinity. Same thing for the minimum y value. That is never attained because it goes down to negative infinity. So the amplitude here does not really apply, so we just write NA. As y max is infinity and y min is negative infinity. We don't actually reach any number. What about the period? When do we start seeing this graph repeat? Well, if I start looking from 0 on to the right, I see an upward parabola followed by a downward parabola. That's not repeating yet because these two are different. And then followed by upward parabola. So this is now a repetition of this part of the graph. So between 0 to 2 pi, that is where we see a unique part of the graph, and then after that we start seeing repetitions going in both directions. So that means that the period is 2 pi, just like what we had for sine. And that is always going to be true. Whatever we have as the period for sine will also be the period for cosecant. What about zeros? Does this graph ever touch the x-axis? Well, the answer is no, because the graph is only these parabolas that either face down or face up or open down. So we never see them cross the x-axis. So actually we have none here. We don't have any. And finally we have asymptotes. Asymptotes are present. They happen wherever sine has zeros. So those would be at multiples of pi. Okay, so the asymptotes are going to be given by x is equal to n pi, where n could be 0, plus or minus 1, plus or minus 2, so on and so forth. The last graph that we're going to be considering for today's lecture is the secant graph. And as you can see here on page 7, one cycle of it has already been given to us. In this case, they plotted points 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the way those are being computed is by considering the cosine graph, because secant is the reciprocal of cosine. So we might as well use it to help us graph secant. So for 0, we get 1 over cosine 0, which is a 1. So 1 over 1 will give us 1, which means that we have to plot the point 0, 1, and that would be this point here. The next point they consider is a pi over 2. 1 over cosine pi over 2 would be 1 over 0, because cosine pi over 2 is 0. Which is going to give us undefined, and that gives us an asymptote. Then at pi, we have 1 over cosine pi, which is 1 over negative 1, and that simplifies to simply negative 1. So the point pi comma negative 1 would be here. Then at 3 pi over 2, we're going to get another asymptote, and at 2 pi, we're going to get 1. Now, of course, these are not enough to draw completely these curves. I mean, there's no way that we can deduce that this curve is going to be the result of that point. So, of course, there are other points that you can plug in, other x values that you can plug in into 1 over cosine x, and ultimately it is going to give you this, this shape. Now, just so that we're consistent with what we used to label the graph of cosecant, I'm going to draw the asymptotes in a dotted blue highlighter, because that's what we use for there. And these graphs then, these parabolas are now, or half parabolas in the case of these two, are going to be the graphs of secant. So let's extend that. And we're going to use that same tip that I gave you guys for the graph of cosecant, meaning we're going to start by drawing the reciprocal function as a reference. Now for secant, the reciprocal function would be cosine, so we'll draw cosine first. Cosine passes through the point 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and 2 pi, 1. That's one complete cycle of cosine. And from there it repeats. So at 5 pi over 2 we reach 0, and then at 3 pi we reach negative 1. Same going in the negative direction. Negative pi over 2 we reach 0, then negative 1, then 0, then positive 1, then 0, then negative 1. So it looks something like this. Okay, so that's the first step. The next step is to draw asymptotes wherever we have zeros for cosine. So we have a 0 at pi over 2, at 3 pi over 2, at 5 pi over 2, at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. And then the last step would be to flip the shape of the reciprocal function. So for instance, between negative pi over 2 and pi over 2, I have downwards facing cosine. So that means that secant will have an upwards facing parabola in that interval. between pi over 2 and 3 pi over 2, we have an upwards facing part of the graph. So that means that we're going to flip it and get a downwards parabola. And so that same principle is going to apply. What you have to be careful is to never have the graph cross the asymptote, because then that means that you actually attain a value at 3 pi over 2 for secant. And we know that that doesn't happen because at that point we get undefined. Okay, so we'll just draw these parabolas, making sure to not cross the asymptotes. Right, now let's look at characteristics. Domain. Well, it's going to be all of the real numbers except where secant is undefined. So from negative infinity to positive infinity, except, well, the places where it's undefined is at these zeros. So except when x is equal to an odd multiple of pi over 2. Okay, so remember, odd number can be represented by a 2n plus 1 and then times pi over 2, where n would be 0, plus or minus 1, plus or minus 2, so on and so forth. Now what about the range? Well, range again is the y values that are reached by the graph. We go all the way down to negative infinity, and then if we want to see what is the highest y value, well, there's a momentary break. Okay, that happens at -1, because from -1 to 1 there's no part of the secant graph. So we go from negative infinity to -1, and then the graph reappears at 1 all the way up to positive infinity. Okay, so don't forget to include the union between those two disjoint ranges. But this is basically saying we can find the graph anywhere between negative infinity to -1, or between 1 to positive infinity. The amplitude will not apply here, just like it didn't apply with cosecant, because we're trying to find the difference between y max and y min, and y max is infinity, y min is infinity. It's not actual numbers, so we can't subtract anything that is not a number. For the period, we want to see where does the graph repeat. Well, again, think about it just between 0 and 2 pi. That was the original cycle that was given to us. That is where we see a unique part of the graph. And then if you start considering this half of the parabola that comes after 2 pi, that corresponds to this half of the parabola that comes after 0. So we start seeing a repetition after 2 pi. Now, if that's a little bit difficult to see, you can also instead consider two whole parabolas. So meaning I could consider the interval between negative pi over 2 and 3 pi over 2, and then see what the distance would be between those two numbers. So if you want to do that instead, what we could do is take 3 pi over 2 and subtract away this negative pi over 2, and that would give us 3 pi over 2 plus pi over 2, because negative times negative becomes positive, which is going to give us a 4 pi over 2, which is 2 pi. Okay, so ultimately the period is 2 pi, whichever way you decide to consider the cycle. Okay. Does this graph have zeros? Does this graph touch the x-axis at any point? It does not. And finally, where do we have asymptotes? Well, we have asymptotes at odd multiples of pi over 2. which is the same as the numbers that we excluded from the domain. So one way to find asymptotes is to always look at the domain and see what was excluded. We excluded the 2n plus 1 times pi over 2, where n could be 0, plus or minus 1, plus or minus 2, or any other integer. Okay, so let's continue then. On page 9, we're taking a look at how to graph the tangent function. So we've been given a list of x values, and we've also been given the corresponding y values already in the form of a point x comma y. So really the only thing that is missing is the work in showing that the y value is indeed what is already listed here. And so that's what we're going to do for this part of the table. So the first x value is negative pi over 2. And we can actually find negative pi over 2 on our unit circle. If you take a look at the unit circle, negative pi over 2 is going to be an angle that opens clockwise, and it's going to open 90 degrees because if you recall, pi over 2 is the same as 90 degrees, but in the clockwise direction is how we get the negative part of it. So that corresponds to a coterminal angle of 3 pi over 2, and the point that's associated to it is 0, negative 1. Now, if you remember from the second definition that we learned for the trig functions, tangent is defined to be y over x. So if we want to find out what is tangent of negative pi over 2, we need to take the y value of the point, which is negative 1, divided by the x value of the point, which is 0. And so we're going to get undefined. Yeah, we're going to get undefined in this case. So tangent of negative pi over 2 is undefined. And that always corresponds to an asymptote, already listed here. Okay, now let's take a look at negative 3 pi over 8. Negative 3 pi over 8 is not something we have on the unit circle. So what we're going to do is we're going to rely on our calculator for that. Make sure that you are in radian mode before you proceed to enter that. So we'll have tangent of negative 3 pi over 8. That gives us approximately negative 2.4142. Okay, which is this y value. If we take a look at the next one, tangent of negative pi over 4, that one you have the option to use the unit circle to help you find, since pi over 4 is on the unit circle. But just because we've already have our calculator in our hands, let me go ahead and punch it in. Tangent of negative pi over 4 is negative 1. So that agrees with the y value there. And we'll do a couple more. We'll take care of these two, and then for the rest of them, we'll trust that these y values are correct. But we'll have tangent of negative pi over 8 gives us negative 0.4142 approximately, which is that y value given. Okay, and we'll do one more. Tangent of 0. Again, 0 is something that's on the unit circle, so you can use it to help you find the y value. But if we punch it in, we get tan of 0 is 0. So that's how we're getting that point. Okay, so for the remainder of the x values, I encourage you to use your calculator to help you verify that these numbers and points are correct. I'm just going to write tan of pi over 8. You want to verify that that's going to give you approximately 0.4142. Tangent of pi over 4, use unit circle or calculator to help you verify that it gives you y value of 1, tangent of 3 pi over 8, verify that it will be approximately 2.4142, and the last one, just verify that tangent of pi over 2, which you can use your unit circle to help you, is going to give you undefined, and therefore will be an asymptote on the actual graph. Before I actually plot the points, I want to consider what x values I need to be able to identify on the x-axis. So what I mean by that is, look at these x values. We need to make sure that we know where is pi over 8, where is 3 pi over 8, where is negative pi over 8, and negative 3 pi over 8. Yeah, so to be able to identify where that is, let's just think about where is pi over 4. Because if you consider what is half of pi over 4, half of pi over 4 is pi over 8. So that means that halfway between 0 and pi over 4, we'll find pi over 8. So where is pi over 4? Well, pi over 4 is half of pi over 2. So if I take half of pi over 2, that is pi over 4. So this would be halfway between 0 and pi over 2. And we said half of that is pi over 4. And then halfway, or half of pi over 4, so halfway between 0 and pi over 4, that's pi over 8. So this is allegedly right in the middle. Okay. So this is like 1 pi over 8. This would be like 2 pi over 8, which reduces down to a pi over 4. This here would be a 3 pi over 8 then. And this last tick mark would have to be 4 pi over 8. Which agrees, because if you reduce that, it gives you a pi over 2. Okay, so we're able to label these tick marks and get multiples of pi over 8. Now if we go into the negative direction, halfway between 0 and negative pi over 2 would be negative pi over 4. And then halfway between 0 and negative pi over 4, we would get this negative pi over 8. So now again, it's just a matter of counting. This is negative 1 pi over 8, negative 2 pi over 8. Halfway would be negative 3 pi over 8, which I'll go ahead and draw up here so that it doesn't interfere with the next labeled tick mark. And then the last one would have to be a negative 4 pi over 8, which if you guys notice, it agrees because when you reduce, it gives you the negative pi over 2. Okay, so now that we've labeled the necessary tick marks, I'll erase these extra markings that we wrote down just to help us verify our work, and let's get to plotting the points. So the first one is negative pi over 2 with the y value of asymptote. So it's actually an asymptote. That is not a point. It is going to be this vertical line at negative pi over 2. Then at negative 3 pi over 8, that corresponds with a negative 2.41. So negative 3 pi over 8, this is negative 2, this here would be negative 3, then we would have a negative 2.5. So if I want to get negative 2.4, it's going to be right above that negative 2.5 line. Okay. Then negative pi over 4 comma negative 1. So here's negative 1. That means we'll get that point. Negative pi over 8 comma negative 0.4. Again, this is negative 0.5. So negative 0.4 is going to be right above it. So it's actually going to go into our label there. Then we have 0 comma 0. 0.8 comma 0.4. So I'm just going to label these in really quick. Okay, this would be this would be positive 0.5. Actually, it's a little bit higher, halfway. So 0.4 is going to be right beneath that line. Then at pi over 4, we reach 1. At 3 pi over 8, we reach 2.4. So here is 2.5. That means that 2.4 will be right below that line. And finally, at pi over 2, we have undefined again, which means we have this vertical asymptote. Okay, so what does this mean for tangent? For tangent, we're going to have a curvy line, or I should just say a curve, that will go down to negative infinity if we try to get to negative pi over 2 from the right-hand side of the x-axis. Okay, so this is just going to continue to go down. And then we're going to pass through these points, and then it's going to shoot up to positive infinity. And the way that we know that is because we have an asymptote, but you can always go in and double check. You can always try to get a value that's really close to pi over 2, but still less than pi over 2, and plug it into tangent. So let's see, like if I do pi over 2, that is 1.5707. So if I tried tangent of, say, 1.56, that gives me 92. If I try to get closer to 1.5707, I can do tangent of 1.5700, and that's going to give us 1,255. So you can see that the closer I get to pi over 2, the higher and higher the number is going to get. Similar behavior is going to happen if you try to get to negative pi over 2. Okay, but this is what one cycle of tangent is going to look like. If we extend the graph beyond pi over 2, so beyond pi over 2, we're going to see this part of the graph repeat. So let me actually just use some highlighters here. So this bottom part of the curve that goes into the negatives and gets really close to the vertical asymptote starts repeating here between negative pi over 2 and pi. And then this part of the curve, which is positive and curves up towards the asymptote at pi over 2, repeats at between pi and 3 pi over 2. So altogether, this whole thing, this curve that's connected between negative pi over 2 and pi over 2, repeats between pi over 2 and 3 pi over 2. Okay. Same if we go more in the negative direction, we'll see that that part of the curve is going to repeat between negative 3 pi over 2 and pi over 2. So just to make sure that it's very clear to us, this is one whole curve that is repeating in those areas, in these intervals. We're going to be using that to help us find the characteristics of tan of x. So what is the domain? Do we have any restrictions of x values that we cannot plug into the tan function? Well, we do have some x values that cause issues, specifically those where we get an undefined answer for tangent. Those happen wherever we have the asymptote. So if you notice, it happens at negative 3 pi over 2, at negative pi over 2, at pi over 2, basically at any odd multiple of pi over 2. So what we can write here is the domain is all real numbers. So from negative infinity to positive infinity, except the places where x is equal to an odd number, and if you remember, an odd number can be represented with 2n plus 1 times pi over 2, where n is representing any integer 0, plus or minus 1, plus or minus 2, so on and so forth. And so that's for the domain. For the range, that is asking what are all the possible y values that you're going to obtain from tangent. Well, from tangent, there is no restriction on y values, right? If I'm gonna, no matter how far negative I get, there will be a part of the graph that touches that negative y value. So I can always look back and see what is the x value that corresponds to the very negative y value that I chose to consider. Same thing if I go up in the positive direction, it doesn't matter how far up I go, I'm still going to be able to find an x value that corresponds to whatever positive y value I'm considering. So the range doesn't have any restriction. It goes from negative infinity to positive infinity. Okay, and then what about the amplitude? Well, if you recall, the amplitude was half the distance between the highest y value or the largest y value and the smallest y value. In this case, the largest y value, so let me just write that, y max, doesn't exist, right? Because it actually goes on to infinity. So this one doesn't exist. And same thing for the y minimum. There is no minimum y value because the graph extends down to negative infinity. So that means that the amplitude here doesn't exist. So we're just going to write NA. Okay, it does not apply, not applicable. What about the period? Well, the period, if you recall, is how long does it take the graph to repeat? Well, I see one unique part of the curve between negative pi over 2 and pi over 2, right? Nothing in the graph there repeats. Everything is unique. It's not until I start considering beyond pi over 2 that I see this yellow highlighted part of the graph repeat. So the period has to be the distance between negative pi over 2 and pi over 2. Okay, so that's what I'm going to write there. The period will be the distance between negative pi over 2 and pi over 2, which means that I'm going to take pi over 2 and subtract away from it negative pi over 2. Okay, this here is the period. And that is going to give us a pi over 2 plus pi over 2, which is going to be pi. And that is very different to what we got with sine and cosine. With sine and cosine, we actually got a period of 2 pi. All right, what about zeros? Where does the graph touch the x-axis? Well, it happens at negative pi, at 0, at pi, at 2 pi. So basically, at any point where we have x is equal to an integer multiple of pi, that's where we will see tangent touch the x-axis. Okay, so this is for n being 0, plus or minus 1, plus or minus 2, or anything greater. And finally, the asymptotes. Where do we have asymptotes? Well, whatever we excluded from the domain, we excluded because we got undefined, and that always corresponds to the asymptotes. So the asymptotes are going to be given by this equation here, and by x equals an odd multiple, so that's 2n plus 1, times pi over 2, where n can be 0, plus or minus 1, plus or minus 2, so on and so forth. So next we are going to consider the cotangent graph. And just like with the tan graph, they've already provided for us the x values they want us to plug into cotangent and the expected y values. So we're just going to verify maybe the first half of them, and then the rest we're going to trust that what they gave us is correct. Okay, but you can always go in and verify by either using unit circle when appropriate or the calculator for any other time. Okay, so for cotangent of 0, since 0 is an angle on the unit circle, I can take a look at what happens at that point. Okay, so this is a 0 angle. Its terminal side did not open, terminal side did not open, so it stayed where the initial side is at. In that case, we're going to get that cotangent of 0 radians is going to be x over y, because remember, cotangent is the reciprocal of tan, and tan is defined to be y over x. So cotangent will be x over y, and if you look at what are the values of x and y, we get an x value of 1 and a y value of 0. So this is going to be undefined. Okay, so here we're going to get, I'm going to write it down, this is a 1 over 0, which is undefined. And that corresponds to asymptote. What about cotangent of pi over 8? Well, pi over 8 is not something we have on unit circle, so we're going to have to use our calculator. And to do so, we can type a 1 over tangent, because remember, cotangent is reciprocal of tan. So 1 over tangent of pi over 8. And that's going to be approximately a 2.4142, which agrees with the y value that they gave us. So it's approximately 2.4142. Okay, again, let's check pi over 4. There are two options for checking pi over 4, unit circle or calculator. In this case, I'll rely on the calculator. We're going to get a 1. So that agrees with a point of pi over 4 comma 1. Let's try 3 pi over 8. Okay, that's approximately 0.4142. Okay, so that's correct. And we'll check one last one, pi over 2. Okay, so this one we want to be careful about, because notice what's going to happen if I try to plug it into my calculator. I'm going to get a domain error, which might lead me to believe like, hey, I have an asymptote here. But that's not actually the case, and here's why. Look at the unit circle. Okay, we're considering angle pi over 2, which means that we're looking here at an angle that is 90 degrees. At an angle that is 90 degrees, or pi over 2, we have the point 0, 1. So that means that cotangent of pi over 2, which is supposed to be x over y, is going to give us a over 1. So 0 over 1 is actually 0. It's not undefined. So cotangent of pi over 2 should be 0. Now, why did we get a domain error on the calculator then? Well, here's why. If we go back to what we punched in, we actually have 1 over tangent of pi over 2. So what the calculator does is it first determines what is tangent of pi over 2. And since that returns a domain error because tangent does have an asymptote at pi over 2, it then thinks, well, if I'm getting an error for that, then I can't do 1 divided by error. Right, so that is why we're getting a domain error at this point. So just be very careful about when you're plugging in cotangent values, because those will always have to verify with the unit circle when it comes to multiples of pi over 2. Okay, so remainder of x values, we're just going to trust that the given ones here are correct, so that if I try to check cotangent of 5 pi over 8, that will be approximately negative 0.4142. If I check cotangent of 3 pi over 4, that's going to be approximately exactly negative 1. You can check it on the unit circle. 7 pi over 8, cotangent of that will give us approximately negative 2.4148. And finally, cotangent of pi, that is going to give us undefined. So you should check this on the unit circle. Okay, basically anything that is 0, pi over 2, or pi, or multiples of those values, check on the unit circle. Okay, so let's plot those, and notice this also has multiples of pi over 8, so I'm going to draw those tick marks before anything. Halfway between 0 and pi over 2, I'll find pi over 4, and then halfway between 0 and pi over 4, I'm going to find a pi over 8. So this is 1 pi over 8, 2 pi over 8, 3 pi over 8. This will be a 4 pi over 8, followed by 5 pi over 8, 6 pi over 8, okay, so 6 pi over 8, but that reduces to a 3 pi over 4, then we have a 7 pi over 8, and finally an 8 pi over 8. Okay, so now that those are labeled in, let's plot the points. 0 corresponds to an asymptote. So we'll have an asymptote here at the beginning. Then at pi over 8, we have approximately 2.4. This is 3. This would be 2.5. So 2.4 is going to be right below that line. Then we have pi over 4, which corresponds to 1. 3 pi over 8, which corresponds to approximately 0.4, so it'll be right below that line. Then at pi over 2, we'll have 0. At 5 pi over 8, we'll have negative 0.4, so about there. At 3 pi over 4, we'll have negative 1. At 7 pi over 8, negative 2.4, so about here. And finally, at pi, we'll have another asymptote. So the curve of cotangent looks more or less like this. Now, what if we extend the cotangent graph? If we extend the cotangent graph, we're going to have that same initial curve from 0 to pi. So let's just draw that. And I know that this is at 1 because halfway between 0 and pi over 2 is pi over 4, and we have the point pi over 4 comma 1. This is 3 pi over 4, and at 3 pi over 4 corresponded to negative 1. And then we had asymptotes at 0 and pi. So I'm going to approximate the rest of the points so that the curve of cotangent follows more or less what we had on the previous page. Okay, so we're going to have this followed by the same 3 points repeating, but now we have, well, this is 1 pi over 4, this is 2, 3, 4, 5, so 5 pi over 4, 6, 7, 8, 9, this is 10, 11, and 12 pi over 4. Okay, so I'm gonna have at 3 pi over 2, you can double check, it's gonna correspond to 0. At 5 pi over 4, we're gonna get a 1. And at 7 pi over, oh, and this should have been a 4. 7 pi over 4, we're gonna get -1. Again, I'm just throwing those points at you, but you can always verify by looking at unit circle or by plugging into your calculator. So I'm going to get this curve, and it's just going to repeat. So I've gone ahead and repeated that process in the negative direction, meaning I verified where I have zeros, which happen at multiples of pi over 2. Odd multiples of pi over 2, I should say. And I also verified that at -3 pi over 4, I get 1, and at -pi over 4, I get -1, that I have asymptote at -pi to confirm that this is indeed the curve of cotangent. Okay, so I encourage you to do the same. Make sure that these points agree for cotangent, and then draw the remaining cycles on this graph. We're going to be using them to help us determine the domain. The domain is basically anything that that can be plugged from the x-axis without having any issues. So that'll be from -infinity to +infinity, except the places where we have asymptotes, because that is where we'll get something that is undefined. So where do those happen? Well, now they're happening at 0, pi, 2 pi, 3 pi, -pi, -2 pi, basically any multiple of pi. So they happen at n pi, where n is any integer 0, plus or minus 1, plus or minus 2, so on and so forth. What about the range? What y values can we attain? Well, just like in the tangent graph, we can attain any positive y value that we want and any negative y value that we want. There is no break in the continuation of the graph if we're considering going up and down. Okay, so the range will be from -infinity to +infinity. For the amplitude, we're going to write NA, because very similar to what we saw with tangent, we have no maximum y value and no minimum y value. That graph extends in both directions forever. And then the period is the place or how long it takes along the x-axis in order for one cycle to repeat, or in order for the graph to repeat. So I can see that one cycle is happening between 0 and pi, and then after that I notice a repetition of the graph. So that means that the period is going to be pi, just like what we saw for tan. Okay, so the period is going to be pi. I'm writing p for the period. Okay, what about zeros? Where does the graph touch the x-axis? Well, that happens at -5 pi over 2, -3 pi over 2, -pi over 2, pi over 2, so on and so forth. So the pattern that they all have in common is that they are odd multiples of pi over 2. So the zeros are at odd multiples, so that's 2n plus 1 of pi over 2, so times pi over 2, where n is going to be 0, plus or minus 1, plus or minus 2, so on and so forth. Okay, and finally the asymptotes. The asymptotes are going to be given by whatever we excluded from the domain, which in this case was x is equal to n pi, where n is any integer. That brings us to the final definition that is part of this set of lecture notes, and that is a definition for even and odd. Okay, we're going to say that a function f of x is called odd if f of negative x gives you the same thing as -1 times f of x. And it's going to be called even if f of negative x gives you the same thing as just f of x. And for both of these, I want to provide you an example. So for instance, if you take a look at f of x equals, and this is an example, so I'll write e.g. f of x equals x cubed, for instance. Okay. If we take a look at what is f of -2, well, f of -2 will be a -2 cubed, which is -8. If I take a look at what is f of 2, I'll get 2 cubed, which is 8. So if I take f of 2 and I multiply it by a -1, that's going to give me a -8, right? So if you notice, both of these are the same answer. That means that f of -2 is the same thing as negative f of 2. For something that is even, and an example could be like f of x is equal to x squared. In fact, let me make this a little more complicated. Let's make it x squared plus 3. If you check f of, let's say, -2 as well, I'm going to get -2 squared plus 3, which is going to be a 4 plus 3, which is 7. And if you check f of 2, that's going to be a 2 squared plus 3, which is a 4 plus 3, which is also 7. Okay, so they both give the same answer. That means that f of -2 is equal to f of 2. And it's not just a coincidence. If you try it for any other x value, checking f of any negative value will give you the same thing as f of the positive value. And in the case of x cubed, if you check f of any negative value, that'll be the same thing as -1 times f of the positive value. Now, graphically, something very special happens. Graphically, what that means, if I were to graph x cubed, and I'll do it here, it won't be perfect, just so that we can get a rough idea of the behavior. If we plug in a 0, we'll get 0. So there's a point at 0, 0. If we plug in a 1, then we're going to get a 1 cubed, which is 1. If I plug in a 2, so this is 1 and 2. If I plug in a 2, we already saw that that gives us 8. So I don't know if it's going to fit, but we're going to try our best. 2, 3, 4. Okay, let's just make that go in intervals of 2 so that it fits. So this will be a 4, a 2. That just means I'm going to move this point a little lower so that it's a 1, 1. Okay. Then I get a 2, 8. So I get something that looks like that. Okay. If you plug in a 3, you're going to get 27, so it's going to continue to curve upwards. If I go into the negative direction, so this is -1, this is -2, I'll have a -1, comma -1. So that'll be about here, okay, because this is now -2, and then -4, -6, -8. And then at -2, well, we'll reach -8. So we'll have this curve. So essentially what we're seeing is that this part of the graph that's positive, if you were to rotate it around the x, so using the origin as kind of like a pinwheel, the center of a pinwheel, and you would rotate that pinwheel, you would get that this bottom half of the graph is the same as this part of the graph, but obviously again rotated. And that's going to be true about any function that is odd. If you take that part that is up in the positive direction, it's going to rotate down into across the opposite quadrant, and it's going to rotate in that direction. For the even functions, the graphs will also have a special property. If I graph y equals x squared, I'll get 1, which corresponds to 1. So I'll have that point. And then 2 is going to correspond to 4, right? 2 squared is 4. If I plug in a -1, I'm also going to get 1. And if I plug in a -2, I'm going to get a 4 as well. And then if I plug in a 0, I'll get 0. So it's a parabola. But what's special about this type of graph is that the points reflect across the y-axis. So what I mean by that is that everything on the right-hand side of the y-axis has a mirror image on the left-hand side of the y-axis, right? These points reflect each other. And the same will be true, it's true about x squared, but it's the same as going to be true about any even function, because by definition, if you take the negative value and plug it into f, you'll get the same thing as the positive value. Okay, so these special properties are called, for even, it's called reflection about symmetry about y-axis. And in this case, we say there's symmetry about the origin. Now we want to see whether the functions that we have talked about so far have any type of symmetry, whether it be odd, even, odd or even. So let's bring back one of our graphs. Here is the graph for sine, and the easiest symmetry to check for is symmetry about the y-axis. If we use the y-axis as a mirror, does the right-hand side of the graph reflect across to the left-hand side? Well, the answer here is no, right? We don't see that type of symmetry. Okay, so it's not going to be even. The next type of symmetry that we should check for is rotation about the origin, or symmetry about the origin. So if I take, let's say, just like this part of the graph, which is going up in the positive direction, and I rotate it about the origin, am I going to get the same curve? Well, the answer here is yes. If you take a look, focus just on this little piece of the graph. If you rotate it in this direction, it's going to come and lie directly above this portion of the sine graph. So it's actually an odd function. In fact, if you take this whole portion of the graph and you rotate it about the origin, you're going to get, well, this part of the graph. So sine is actually an odd function. So here we're going to select odd, just to test some points and verify that that is indeed the case, because we did it by looking at the graph, but we could also just take some points and verify. If I take, for instance, f of pi over 2, meaning if I plug pi over 2 into sine, well, sine of pi over 2 is going to give me a 1, right? So this is 1. Now if I check what is f of negative pi over 2, meaning if I plug in negative pi over 2 into sine, here's negative pi over 2. For sine, we get a negative 1. So I get negative 1. What we need to check then, is it true that if I take negative of f of pi over 2, that is equal to f of negative pi over 2? Are those two going to be equal? Well, here we're going to get a negative times 1, a negative 1 times 1, and that is equal to negative 1 for f of negative pi over 2. That's a check. So yeah, this even though we've only tested with 1 point, and that doesn't necessarily prove that it's odd in all cases, it does give us a good hint that it might be odd. And then we go and verify by looking again at the symmetry of the graph. Okay, what about for cosine? Well, for cosine, if we look at the graph, for cosine, we said the easiest symmetry to check for is symmetry about the y-axis. If we use the y-axis as a mirror, is it true that the right-hand side of the graph reflects across into the left-hand side? And well, the answer here is yes. If you take a look at this part of the curve, it's reflecting directly into this part of the curve. And then the part that's between pi over 2 and pi, we see it reflect here between negative pi over 2 and negative pi. So again, from the graph, we can judge that it is going to be even, but we can just take a look at some points. If I try, for instance, let's say f of pi. F of pi gives me, or cosine of pi gives me negative 1. And then if I plug in f of negative pi, well, here's negative pi. It also gives us negative 1. Okay. So in this case, f of pi indeed equals f of negative pi. So we can just, again, it doesn't prove it, but it confirms to us that that cosine is an even function. And we're going to consider one last graph, which is tangent. Okay, here's the graph. And if we focus on reflection about the y-axis, we use the y-axis as a mirror. This part on the right-hand side does not reflect over on the left-hand side, otherwise it would look like a parabola. But if I take this top portion of the graph and reflect it about the origin, I would see that it would lie directly above this portion of the graph. So we have the suspicion, or from the graph, we can pretty much see that it's going to be odd. But again, we can just test some points. Let's try f of pi over 4. Tangent of pi over 4. Tangent of pi over 4 is 1. And now if I try f of negative pi over 4, well, tangent of negative pi over 4 is negative 1. So if I take -1 times f of pi over 4, I'm going to get a -1, right? Because we'll have a -1 times 1, which is -1. And that is indeed equal to f of pi over 4. Okay. So that means, or that confirms to us that tangent is odd. So these ideas of even or odd are going to be very important for the remainder of the topics that we address in our trig class. So please make sure that you remember these facts and that you also know how to verify their symmetries.